All right, welcome to the lecture 23, concavity and second derivative tests. Okay, so the idea is the following. Let's see so if a function increases, so there are two ways the function can increase, right? One way is like that, right? So this function is increasing as well. And other ways like that as well. So both of these functions are increasing, but the shapes are slightly different. So the function can increase either like this or like that. Similarly, a function can decrease either in this format like that or that format. So you notice there's a difference between the shape of the graph, right? In this case, it's like that, and the other case, it's like that. So now, how can we determine in which way the graph of the function curves? Like, does it curve like this or does it curve like that? Both are increasing in this case, right? So let's try to understand that by looking at a very special example. So let us study the tangent slopes of function y equals to x cubed. So as you notice, the curvature changes at x equals to 0, right? It's increasing in both the cases. In this case, it's curved in this format. We'll choose to call this format as concave down. The cave, the cave is down. Yeah, so this is concave down, concave down. And we'll choose to call this shape as concave up. So here it's concave down and this it's concave up, right? So let's investigate what is happening and what is different in both the cases. So how do you distinguish between these two things? So notice that on 0 to infinity, sorry, minus infinity to 0, let's see what happens to the tangent, slope of the tangents, right? So notice that here the slope of the tangent is positive because the function is increasing, and then it basically reduces down to become 0 here, right? Do you agree? So on minus infinity to 0, the tangent slopes are decreasing as we move from left to right, right? Now consider from 0 to infinity, this shape here. Here the tangent slope was 0. And then as you see, the slope of the lines is increasing. Or here 0 to infinity, the tangent slopes are increasing from left to right, right? So we can generalize this scenario. We can generalize this analysis by saying the following. So this shape was concave down shape here on this part. So a function is concave up. This part was concave up. If f prime is what? You saw that here again. Let's analyze this case again. What happens is the tangents are basically, the tangent slopes are increasing, right? But tangent slopes are encoded in derivative. So we say the function is concave up if f prime is increasing on the interval AB. So we're talking about an interval. So similarly, a function is concave down on interval AB if f prime is decreasing on AB, as you saw in this case here, right? As in here, you saw that it was earlier positive and then it basically decreases down to become 0. So so this is the idea about concavity. So let's go through this again. So y equals to f of x be a differentiable function on an open interval AB, then f is concave up on open interval AB if f prime a is increasing on AB, and if f prime a is decreasing on AB, then it's concave down. Okay, so this is the idea behind concavity and the derivative being increasing or decreasing. However, note the following. I can dub the same thing in the following way. So if a function is decreasing, If a function is decreasing, then the derivative of that function is less than 0. So if f prime is decreasing, then f prime prime is going to be less than 0 on AB, right? Similarly, if f prime is increasing on AB, f prime as a function is increasing, that means f prime prime is going to be greater than 0 on AB. But what is f prime prime? It is f double prime. That is the second derivative. So if f prime x is greater than 0 on AB, then we get the function is concave up on AB. And similarly, f double prime x is less than 0 on AB, then the function is concave down, right? So this is the criteria, and this is the proper characteristic on how you can use the second derivative to find the interval of concave up and concave down. So let's move on ahead. So let's repeat the same thing here. So if f prime is basically, if f prime is a function itself, and if f prime is increasing, that means f prime prime, which is f double prime, is greater than 0. And similarly, if f prime is decreasing, then we have f prime prime is less than 0. So here is a test. It's called second derivative test for concavity because you're using the second derivative of your function. So suppose f y equals to f of x be a twice differentiable function, right? Because you're looking at the second derivative. So first of all, second derivative should exist to talk about, so that we can talk about it. So if f double prime is greater than 0 for all x belonging to AB, then f is concave up. Smiley face like that, second derivative greater than 0. And if f double prime x is less than 0 for all x in AB, then f is concave down on AB, like a frowny face, second derivative less than 0. So then the question is, if you are given a function, how do you determine in which interval it's concave up and in which interval it's concave down? Note that you'll be usually interested in basically the what the open intervals in which it's concave up and concave down. Okay, so here's the guidelines. So suppose your y equals to f of x is a twice differentiable function on its domain. So find all the critical points of y equals to f prime x. These are not necessarily same as all the x values where function is undefined, all right? These are the x values section the domain into what? And open intervals, all right? And now for each of these points, apply the second derivative test for concavity to see each number n to decide if f is concave up or concave down on this interval, all right? So let's see. So how do we go about it? We start with the critical points of y equals to f of x. So let's see here. So at any values of x in the domain of f, the tangent line, where the tangent line exists, it's either what? It's either vertical, like that, right? Same here, or basically is a point where the concavity changes. So you see here the concavity changes. So here the concavity changes, right? So how do you find out such points at which the concavity changes, right? So here, if you notice, the function changes from concave down to concave up. Similarly here, the function is concave up and then it becomes concave down. Similarly here, the function is concave down and then it becomes concave up. So all these points here are special points. They are what are called as inflection points. So these points are inflection points. Where the function changes from concave down to concave up or concave up to concave down. Now the question is, how do you determine the inflection points? So first, what you do is the following. You basically compute f prime x and f double prime of x. Then find all the critical numbers c of function y equals to f prime x. Determine the sign of f double prime x from left to right at the point C. If there's a sign changes, then C is an inflection point. Okay. So basically the idea is we are concentrating at the critical numbers of the function y equals to f prime x instead of basically y equals to f of x. Okay. So let's move ahead and notice let's do the following problem. So we'll apply the guidelines for the concavity here. So we'll differentiate this function twice. So you're taking f prime x, which is going to be 3x squared plus 12x minus 15, and take f double prime x, which is 6x plus 12. Now we need to identify the critical points of f prime. All right, note f prime, not f double prime, and x values where f is undefined, both. All right. So now let's see. So f double prime x is equal to 0 implies 6x plus 12 equals to 0, which gives me 6 times x plus 2 equals to 0, which gives me x equals to minus 2. And f prime basically, and where is f undefined? Well, f is defined everywhere, so we don't have to worry about that. So f is defined everywhere, so there's no contribution from undefined part. Now what we'll do is we'll look at the sign chart for f double prime. So we'll look at the sign chart, because if the sign is positive for f double prime, then the function is concave up. And if sign is negative, then the function is concave down, right? So pick a point of your choice from here. So let's say minus 3. If you take minus 3, substitute in this equation. So you get what? So if you take minus 3, a double prime of minus 3 is going to be minus 3 times 6, which is minus 18. Minus 18 plus 12 is negative. So this is less than 0. So here the sign will be negative. Similarly, let's take a point here on the side. Let's take 0. F double prime of 0 is greater than 0. So here the function, the sign for f double prime is positive. And this would mean that your function is concave down here and here. So concave down like that, and here it's concave up. The shape will be like that. So therefore, by second derivative test for concavity, f is concave down on minus infinity to 2 and concave up on minus 2 to infinity. So since the concavity changes at x equals to minus 2, x equals to minus 2 is gives us an inflection point. So namely, we'll get minus 2, f of minus 2 is an inflection point. Okay, so this is the idea behind the inflection point. So now there's an application of this in economics. This is called law of diminishing returns. So the law of diminishing return in economics is related to concavity. The idea is the following. Let's see. So here your function is basically increasing and you're still increasing. So this quantity is still increasing, but here you see it's increasing quite fast and relatively it's increasing quite slow here. So there is a diminishing returns. I mean, the return is still positive, but it's diminishing. So that's the idea behind it. Okay. So the graph, so let's be given the following. So graph of function gives an output y. Say suppose some output of object y in terms of input x, right? Now, for example, if inputs were advertising cost, cost of some product, then output could be the corresponding revenues from the sales. Yeah. Or for example, the input could be the amount of sugar and output could be the amount of the yeast basically, created out of fermenting that sugar, right? So now the graph shows an inflection point at what, so you see here it's concave up and then it becomes concave down. So this is your inflection point, C comma f of C. So it shows an inflection point here. So if x is less than C, the graph is concave up, which means the output y is increasing at a faster rate with each additional dollar spent, right? Similarly, for x greater than C, so somewhere here, as you see, the graph is concave down, which means the output y is increasing at what is basically is decreasing at a faster rate with each additional dollar spent in the producing a diminishing return. All right. So the return is still positive, but the idea is the output, the rate of output is decreasing, right? So therefore, point C comma f of C is referred as point of diminishing returns. Okay, that means what? So the output is basically in this case is basically it's not increasing at the same level as it was increasing here. So the returns are diminished. So let's do an example here. So so suppose a certain country's consumer price index CPI between 1990 and 1999 is approximated by I of t equals to this function. Your t is between 0 and 9. Determine the inflection point. So we'll apply the guidelines for concavity. So we'll differentiate it twice. So I prime of t is going to be minus 0.6 t square plus 60, and then I double prime of t is going to be minus 2 point t plus 6. Now we identify where I prime, critical points of I prime, or where the second prime becomes 0, or where the values of t where I is undefined. But it's a polynomial, so it's defined everywhere. So I double prime of t equals to 0 implies minus 1.2 plus 6 equals to 0. This implies t equals to 6 divided by 1.2, which is going to be 5. And I is defined everywhere. So there's no contribution from that part, the undefined part, right? So now what we need to do is we need to determine the sign chart for f double prime, sorry, I double prime, to see whether the 5 gives us a inflection point. So take a point of your choice here, say it's 0. So if you take 0 and you substitute here in I double prime, you'll get 6. So here it's positive. Take a point of your choice here, say 6. So if you put 6, you get minus 1.2 times 6 plus 6. And that is already negative, right? So here you have negative. So by second derivative test, you can see that so second derivative test for concavity, you can see that I is concave up on 0 to 5, 5 excluded, and concave down on 5 to what, 9. And in this case, since the concavity changes at t equals to 5, this is called an inflection point. So what is an inflection point? Your inflection point will be 5 comma I of 5. Okay. So when you substitute that, you'll get the inflection point. All right. So now We can also use the concavity to find out relative maxima and relative minima. So let's see how. So first, recall on basis of first derivative test, if the derivative changes sign from what? From positive to negative at a critical point, then there is a what? A relative maxima or relative minima. Let's just draw it. So what is happening? At critical point, it was positive, the derivative was positive, that means the function was increasing. After that, the derivative became negative, that means the function started decreasing. So it will give you relative what? Maximum. And similarly, if it changed from negative to positive, then you'll get relative minimum. If it changes from negative to positive. So now, however, we can also use our knowledge of concavity here to test for relative extrema at a critical point. Let's see how. So first of all, the first ingredient is that this C is your critical point. All right. So you're not testing at any point. C is a critical point. Now notice the following. So C is a critical point. However, the graph is concave what? Concave up. So F double prime C is greater than 0. And what you're getting really is the relative minimum. So we have F has relative minimum at C. Right? So what do we need? We need that C is critical point and F double prime C is less than 0. Then we get what? Sorry, greater than 0 in this case. We get relative minimum. Similarly, notice the following. In this case, you have C is a critical point. That is the first qualification. And you see that the second, this is concave down. So the second derivative of C is less than 0. And you're getting what? Relative maximum. So F has relative maximum at x equals to C. Okay. So this gives you a second derivative test for relative extrema. All right. So let's rewrite it. So compute. So suppose y equals to f of x is a twice differentiable function, right? The reason for twice differentiable is we are using the second derivative test. So this is only applicable where the function has the second derivative. So what you do is first you compute f prime x and f double prime x. Then you find out all the critical points of your y equals to f of x. That means that f prime equals to 0, right? Because it's twice differentiable, we are excluding the case where f double prime c does not exist, right? Now compute the second derivative at such points. Yeah, only at the critical points. If the second derivative is less than 0, then the graph has relative what? Relative maximum at c. Yeah, because this is how the shape is going to be at relative maximum, and you see it's concave down, right? Similarly, if f double prime c is greater than 0, then f has relative minimum at c. However, if f double prime c is equal to 0, then the test is inconclusive. So we must use some other methods to find the behavior of curve at c. Now note that the first derivative test is robust, means it will work all the time. But second derivative test can be quick in finding the, if it works, is the quicker method in finding the relative maxima and relative minima, right? So note that the second derivative test for relative extrema is inconclusive if f double prime c equals to 0 for critical number c. This tells us nothing when f double prime c does not exist, right? Okay. This also tells us nothing when the critical point c has f double primes, sorry, f prime. So at critical point c, f prime c does not exist, right? So those also you can't really use the second derivative test because you are deciding if the second derivative is less than zero or greater than zero. But if the first derivative does not exist at a point, there's no hope for having second derivative at those points. Nonetheless, as I said earlier, if the second derivative is easy to compute, then this test is efficient or faster in computing the relative extrema. All right. Okay. So let's do a problem on this. So you're given the following function. Use the second derivative test to classify the critical points of this function. So let's find the critical point first. So take f prime x. We have 3x squared plus 12x minus 15. So it's a polynomial, so critical, all the derivatives exist, right? So f prime x equals to 0. So we want to solve for that, not for does not exist case because the derivatives always exist in this case. So x squared plus 4x minus 5. So this gives me 3 times x minus 5 times x plus 1. So f prime x equals to 0 will give me that x is either 1 or x is minus 5, right? Sorry, plus 5 minus 1, my bad. So these are my critical numbers. So now we need to evaluate the sign of second derivative at this critical numbers. So let's first find f double prime x. So we get f double prime as a derivative of f prime, which is going to be 6x plus 12, which can be seen as 6 times x plus 2. Now we'll evaluate f double prime x at what? At the critical numbers, at the critical points, and compare. We get what? Compared with 0, f double prime of 1 is going to be 1 plus 2, 3, 3 times 6 positive. So this is going to be 18, so greater than 0. Similarly, f double prime at minus 5 is minus 18, which is less than 0. So therefore, by second derivative test for relative extrema, x equals to 1 is a relative minimum and x equals to minus 5 is a relative maximum. Yeah. In fact, you'll notice the shape more or less looks like this. So we'll later on see how to sketch the graph of the function, but the shape of the graph is somewhat like this. At 1, we have relative minima, it's concave up like that. And then the concavity changes at what point? We already have done this problem earlier. So the concavity changes at somewhere here at minus 5. Oh, sorry, this is a different function, right? So the concavity changes at some point here, and this is how at 5 you have a relative maxima, and then it basically goes down like that. Okay, so we'll be able to draw the graph of this very soon, particularly when we go on to the next part of the lecture, which is about curve sketching. All right, so here's a summary. Let's go through it. So if f prime x is greater than 0 and f double prime x is greater than 0, then what happens? What is the general shape of the graph? F prime x is greater than 0 means the function is increasing and it's concave up. So the graph will more or less look like that, right? It's concave. If f prime x is greater than 0 and f double prime x is less than 0, then the function is concave. is increasing but concave down manner. Similarly, if f prime x is less than 0 and f double prime x is greater than 0, then f is decreasing, but f is also concave what upward. So it's like that. Next one is if f prime x is less than 0, so its function is decreasing, and f double prime x is less than 0, then function is concave downward. So if I combine this, it will be decreasing function but concave downward. So these are the shapes of your graph. All right. So that's all for today. Thank you.